let's consider a tale of two buses. This first school bus, it has a mass of 20,000 kilograms and is at rest. And we want to know what would happen to the bus's acceleration if we pulled it with greater and greater force. So at the beginning with this bus at rest, we pull it with a small force and we measure the acceleration of the bus at that force. We would find that at a very small force, the acceleration would be pretty darn small. So I'm going to put a dot on my acceleration versus force graph. And then I add a greater force, maybe this much, and I measure my acceleration and I notice that the bus now accelerates a little bit faster, right? So I put a dot here. And then I pull with a greater force, and I notice that the bus accelerates more. And then I pull with a very, very large force, and I notice that the bus accelerates a ton, right? If I draw a trend line, I would notice that the line is straight, moves up and to the right, which tells me that the acceleration is directly proportional to the force. And in math, we can write that this way. Acceleration is directly proportional to the force, which means that if I was to double the force, I would get twice the acceleration. And if I was to triple the force, I would get 3 times the acceleration. And if I was to multiply the force by a factor of 10, I would get 10 times the acceleration. So we say that the acceleration is directly proportional to the force. Now let's go to the same bus, but in a different scenario. Okay. Now our bus is going to start with a very, very small mass. So before the mass was 20,000 kilograms, but now let's say that the mass is almost zero, that it has extremely tiny mass. But we are going to pull this extremely unmassive bus with a force of 10,000 newtons. Well, what would happen to the bus's acceleration then? So if you pull a very, very, very tiny object, low mass object with a huge force like this, you would expect to get a really large acceleration, right? And so tiny mass, large acceleration, the first dot on my graph would be like way up here. And then what if I start to add some kids onto this bus, right? So I start increasing the mass of the bus. So and I'm just going to show that by like filling up the bus with a little bit of mass, okay? A little bit more mass with the same force would cause my bus to accelerate a little bit less. So maybe now down here. And then I fill up the bus with a little bit more mass. And I measure the bus's ability to accelerate now. Same force, but my acceleration is going to drop. And I keep filling it up, right? More mass, less acceleration. And then I fill it all the way up, put all the kids on the bus, and I would notice that the acceleration would be quite small. But then let's say that I had a bus that was really, 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 really massive, like the mass of the Earth. But I was only pulling it with 10,000 newtons of force. What would I expect to happen then? Well, if I pulled something as massive as the Earth with only 10,000 newtons, I would expect to get an extremely small acceleration, like an unnoticeably small acceleration, okay? I would expect to get, and I'm going to pull this over a little bit, I would expect to get maybe an acceleration with a really, really massive object. I would expect to get a very, very tiny acceleration, so something like way over here, okay? And so we see if we connect a trend line that it's not a linear relationship, it's actually a curve like this, okay? This is called an inverse relationship, right? An inversely proportional relationship. So we say that the acceleration is proportional to 1 over the mass, which means that if I have 10 times as much mass, I would now have 1/10 the acceleration. And if I have 1,000,000 times as much mass, right, going to the mass of the Earth, I would have 1,000,000 times smaller acceleration. This is how an inverse relationship works. So if I put these two relationships together, right, the bus in the first situation showed me that the force and the acceleration are directly proportional. Doubling the force yields twice the acceleration, but that the mass and the acceleration are inversely proportional, so that doubling the mass would give me half the acceleration. I can combine them, okay, into this. The acceleration is both directly proportional to the force and inversely proportional to the mass. And this is famously known as Newton's second law. The only thing that we would add is to clarify that this force is the net force, right? The sum of all forces acting on the object. And Newton's second law is famously rearranged. So if you multiply both sides by mass, you would get this form, that the net force is the mass times the acceleration. And this is what you would see a lot in most textbooks.